All right, let's see what you remember. Here we go. Are you ready? Okay, ladies and gentlemen. Jasper starts off by telling us anything at all that you know about this function. Go. Can you say that again? What kind of asymptotes? Vertical are at what? And what are the equations of those asymptotes? And how did you find them? Okay, yeah, so, and how does that factor? How does that factor? Okay, I still have some questions, but I think I'll let you slide there. Is this ringing a bell here? All of you, it's all coming back to you. Rithik, give me something else. Anything else you know about this? Let's kill the side conversation if you guys don't mind. Okay, and walk me through that too. Okay, okay, I'll go with you on that too. I got to think about why that makes sense, but I think I like it. No one seems to be complaining, at least. Yeah. No. It's Varun's turn. Sorry. Give me something else you know, Varun. If you can give me anything else. What are we still looking for? If there's another asymptote, maybe that we could talk about, that would be cool. Or are we missing any intercepts we could talk about? How about the y? Do you know the y-intercept? Okay. We'll save a special question for you later. Okay. What about Shine? You look excited about this problem. You want to tell us anything else you know?
Oh yeah, so the y-intercept is 3 over 10.
Okay, y-intercept is 0, 3/10.
Yeah.
And how'd you get that?
Just plug it in.
You plugged in 0. Okay, like any function that anyone ever asks for the y-intercept on. Yeah, exactly. I'm with you. Okay. Daniel, you want to pick up the slack here? What are we missing?
There's a horizontal asymptote at y equals 1.
Okay, and yeah, I do kind of want some reasoning around some of these things, maybe too. So let's go back and give some reasoning. You want to start? Yeah.
Yeah. So the coefficients of the high school polynomials are both 1. So if you make that into a fraction at the end. So
Okay.
You make
And there's like some rule that says that that's how it works or something? Okay. So we're like appealing to a rule that maybe we remember. All right. I have more to say about that in a second here too. The y-intercept, I mean, it's already, there's not much to explain there. By definition, it's the value of y when x is 0. So like we're done there. I think I'm convinced. The x-intercepts, you want to justify why they are what they are? Like why? I understand the procedure. I know exactly what happened, but why are those the x-intercepts? Yeah.
So you got linear factors, and if either of them is equal to 0, then the function is equal to 0. So you just plug in whatever value to make that.
And the other thing I need to know, I guess, too, is that the only way to make a over b 0 is by making a 0.
Yes.
Is that, you hear what I'm saying? Maybe there are more too, right? Like maybe there's another sneaky way to get 0, right? I don't know. So something to think about here. The only way to make a fraction a over b equal to 0 is by making a 0. If we agree to that, then I think I can move on. We might have to think about that, but I think I agree with that. And then what about the vertical asymptotes? Why are they what they are? I mean, kind of I hear what you're saying. Those make the denominator 0, but by making the denominator 0, is that the definition of a vertical asymptote? Is like when the denominator is 0 of something? I mean, we got to maybe go back to the definition. Yeah, you want to help out?
That's kind of work. And then the denominator is 0, it's impossible to divide by 0, then there isn't an f of x value for the x values 5 and -4. And I think that's the definition.
Yeah, is the vertical yeah? What is the definition of vertical asymptote? We should figure that out. It's not defined there. That's you've made that clear. Like this function is not defined at those two places. So that may be an inclination. I mean, we're right, obviously, but yeah, say something more, Graham.
Like as you plug in a value for x that's closer to 5, then the denominator gets smaller and smaller, which makes the value larger because the denominator is smaller. So it reaches closer to infinity or negative infinity.
Right. That's the invoking the definition of vertical asymptote. We desire that it be true that as we get close, we had this notion. Remember we talked about it last unit. This notion of like a one-sided limit, right? So we have like the limit on the left and the limit on the right. As we get close to x equals 5, Grant is saying, for example, from the left or from the right, we get values for y that are either infinity or negative infinity, right? Do you remember that was our definition of a vertical asymptote? You can go back and look at it. It's a limit definition, isn't it? Okay. So now, is it always true that when the denominator is 0, that is going to be what happens? I mean, it seems to be true. We might need some more theory there. But anyway, I mean, we're right here. I just want to kind of press on some of those a little bit. For example, I'd love for you to just try the following. Would you be willing to do this for me? This does actually say, oh, I just added an extra x in there. Got carried away. Could you guys do this for me just for fun? Tell me what you get. Here, I'll write it out. I mean, I just want to have it written the way it is up there, right? This thing divided by this thing, right? I'm just curious what you get. We did this on Friday actually with a cuter example with yeah.
The thing that's supposed to be the denominator is not like it's x squared minus x minus 1, not less x.
Oh yeah, you're right. Sorry. I meant to write exactly what the problem says up there. Sorry. So carry on. That actually doesn't matter for the thing we're going to talk about here. So. And when you're done, give me a rewrite, please, on r of x. That is, rewrite the original function in a new, interesting way. That's going to be a lot faster, a lot efficient, right? Yeah, that's not good. Good.
This is terrible.
I mean, you do you, but you're welcome.
Make sure I got this. I tried to do it on notes. I tried. I need an Apple Pencil now. That's a pointer. No, that's my cousin.
What'd you get?
Oh,
Did you do it? You finished it? Right, can you do the one there? So, yeah, just report your answer in fraction forms, I guess they call it, right? Ruben, do you want this to be your chance to redeem yourself?
Is that one
Huh?
oh crap. Is that one polynomial form is like, would be like, x plus 14 times thus it's just going to be
All right, so tell me how to write this. So in fraction form, what was the quotient? What'd you get? 1. And then what do we write? How does this work? How do we rewrite this expression? We write this is equal to 1 plus what'd you get for the remainder? Is that what you guys got to? 2x plus 14?
Yeah.
Okay. Over. All right. So I think we did it. That's what we're saying is that this function could be rewritten this way, right? Okay. Now, how does that connect to something in this box over here? You see something sitting there that's interesting? What do you see that maybe you don't see in the original form? Yeah, Crystal.
I noticed that the remainder has +1 and then the horizontal asymptote is at 1.
This is not the remainder, but I hear you. It's called the quotient. But yeah, so she sees this and she's like, that's this. And that will always be the case, right? But why? Why does that make sense? Well, because what happens to this guy, that is this portion of R of x, as x grows large? Again, let's appeal to the definition of a horizontal asymptote here. By horizontal asymptote, we don't mean like a thing that it gets closer, or a thing that it doesn't cross, or I don't know what the wrong conception of horizontal asymptote you have in your mind. What we mean is, as x grows large, y approaches this number, right? Isn't that what we mean? So let's try and justify what's going on here. This portion, as x grows large, what happens to the thing I circled? As you plug in, and this might, yeah, I mean, this it might take a little bit of justification too to convince you that as you put in values like 1,000,000 or 1,000,000,000 for x, that this goes to 0. But yeah, this piece here goes to 0. It's got something with an x squared in here that's growing faster than something linear on top. So I think it's pretty clear that this just goes to 1. Okay. The reason I spent some time there is because that was also true on this one here. We did the same thing, didn't we? In order to reveal the feature of the graph here. We said, can't we rewrite this way? Again, what's the horizontal asymptote here? It's y equals 3, right? Down at the bottom. So I hope you're starting to see why that's like a helpful rewrite. And it makes it clear why the rule works too. I think a lot of us know that rule. Oh, if the degrees are the same, then the horizontal asymptote will be just y equals that constant, whatever the two numbers are. But I think you'll start to see that if we always did this, then that's what we'd always get right here. Kind of makes me think too. Yeah, I mean, if we have something of 1 degree divided by another degree, we always get something that's a constant, don't we? Y equals 1. What if we did this same procedure? I want you to start thinking about this. If we had something that was cubic divided by something that was squared, what do you think the star here would be here? What would the quotient be? It wouldn't necessarily be y equals a number. It would be, yeah, it might have still an x in it, right? And then in some sense, would that be the asymptote? The answer is yeah, we're going to go there. So I just want to like start that thought process in your mind. In fact, let's say it right now, okay? All right, so on this slide and the next, we're going to put in boxes all the things you know. I just wanted to take a little time to push on like the quote-unquote rules a little bit, because I know a lot of you come in knowing the rules I'm going to show you here on the next 2 slides. But I want to make sure you really fully understand what you're getting into, what you really mean, okay? Now, just so you're not scared, this first thing up here is just, again, you know how we wrote the polynomial the first time when we introduced polynomials earlier, 2 weeks ago, whatever that was. We talked about this is like our general form of a polynomial, and this is too, so therefore we have it, in fact, in our possession a rational function. And remember, we're lazy mathematicians, so we're just like, I don't feel like coming up with letters for all the coefficients. Let's just call them all A. Or in the denominator, let's just call them all B, right? So, and we'll substitute them. So don't get too carried away or caught up in that notation. We're just talking about a garden variety rational function. So now I'm finally going to come along and say what Daniel said here. If the degree by n is less than m, I mean if the degree is less on top than on the bottom, then we have y equals 0 as our horizontal asymptote. And this is the case that we were just looking at. If the degree n and m are the same, then we have just y equals the coefficients, the ratio of the two coefficients. But again, that should now not just be a mystery or something someone told you. I think you now have some reasoning to support that after the last slide and our discussion about division and how that connects here. I hope you see that connection. But that connection even gives way to a more general claim, which is shown here down at the bottom. In fact, the last two bullet points, in fact, all of them could be combined to just say the asymptote is the quotient of f divided by g. All of these could be encompassed in that, actually. Sometimes it's a constant when you divide it, and sometimes it's not. That's just the deal. You could just summarize it with this one statement, actually. So we'll study in particular slant asymptotes when the quotient you get when you do that division problem we just got. If you get 1, then it's a horizontal asymptote. But if you get something else, like say you get 2x plus 1, that's the quotient, right? Well, then that's our asymptote. Y equals 2x plus 1. So we'll be okay with that, and we'll do some of those. We'll do one example of these today. Okay. And notice that instead of calling it the end behavior, the horizontal asymptote, we've renamed this box we're calling the end behavior asymptote. For that reason, it could be like something besides something, a horizontal asymptote. In fact, if the quotient was quadratic, are you saying that it would approach a parabola as x gets large? Yeah, that's what we're saying. Yeah, it would get closer and closer asymptotically to some parabola, right? That's what we're saying. Yeah. Well, the hyperbola is not a rational function, but maybe we could think about, well, for very special cases, like 1 over x happens to be a hyperbola, and there you could use this kind of thought, I guess, but that's not turned. It's not got a. Yeah. I have to think about how we could connect those ideas. Okay, as usual, these I've copied directly from your book and they're on the Google Classroom already. All that. So I'm going to skip off this slide in case. Okay. Okay. 3, 2, 1. Take a picture if you like. Okay. All right. Let me put the other boxes that are from the book up here too. That was the mind-blowing one. These are not too big of a deal. They're just the exact same things we just said a minute ago, right? Vertical asymptote is what you guys said. X-intercepts, it's what you guys said. Yes. Again, I hope you understand the reasoning around those things. Notice the caveat in parentheses, the parenthetical comment on both of these boxes, though. No one kind of mentioned that, but it is important that we don't just get carried away here. The parenthetical comment is actually important, and I think maybe some of you remember why. I don't know. The y-intercept, I have nothing to say there at all. Okay. There you go. And then I have one more box, I promise, that's going to fit at the bottom here. What is it going to say? Given that I haven't addressed this parenthetical comment yet. Yeah, we should mention holes as well, or as we call them in Unit 1, removable discontinuities. You could call it either one if you want to sound fancy. Okay. And that's the situation that we were kind of avoiding up here in box 2 and 3. I will just say right now, though, that your book, for some reason, I don't know why, I feel like it's a gross omission. It has all these boxes in your books, and I think I really did. I think I put them word for word in your book. Except it omits box 5. It just fails to mention holes at all. I feel like it's like, well, maybe if we don't mention it, no one will notice or something. I might even call it like kind of a hole in their coverage of the topic. It also, problems, rational functions that involve holes are absent completely from the exercises. So let me also take this moment to instruct you on the homework tonight. It's homework 5, but also notice that on your assignment sheet, which we never normally do, there are a couple extra problems on the assignment sheet actually. Okay, so make sure you make a note of that, okay, and actually do a couple extra problems that are there. And just, there might be some foreshadowing here. A couple of those might have holes, right? Just because the book doesn't have them, so I was like, we need to expose you to some more of those. Yeah, we got to make sure you know what you're talking about. Isn't that terrible? They don't have holes in the book. All right. So there it is, all in boxes now. It's what you said earlier, but it's like more official now because we put it in boxes. Right? Now you know what you're reading.
Well, we always do it everything in sense, just to make it even more official.
0. All right, let's do a little more practice here. If you guys would direct your attention, I'll just tell you right now, a little bit of a spoiler alert, this does not yet have a slant asymptote, okay? I know you're excited about getting to that position in your life where you're like reasoning with slant asymptotes, but that's not yet here. This should still be somewhat review. I just wanted to step it up just a little bit. One notch here. Go ahead and, with your friends, graph this function. Or with the people at your table, whatever they are, okay? Check each other on this. Work together to factor those, whatever it takes. And then when you're ready, graph it. I know, I'm sorry. I was doing it quick. By your own.
I thought I
Would we be allowed to use theory cascades? Wait, so what are the factors x?
3 and negative.
I know, right? Where did you get this down? How could I make this a part of my life?
Crossed out version.
Those are compounds that are only 11 months away.
So when I try to find the y value,
No, I can organize this.
My brother called me a nerd when I told him I got my letters mixed up. He's like, nerd. I know, yeah, he's just like calling nerd.
My dad calls me a nerd.
Wait, so X minus X plus 1 is not it's not a number that I'm trying to
The whole of 3. And then it's just like, it's going to be a 2-way variable.
so maybe you should put it in 1 and 1.
Which would give you the which you went up
Two opted out of this. We're just so that way we don't have to go back and put 2 into the original equation. No, we do. I mean that it only has
but that's still
The degree is technically 1 over linear.
No, the top is smaller than the bottom.
Oh, I mean, it's interesting for sure. Can you write the factorization of the numerator and denominator somewhere?
What was it again?
Minus 2 plus that minus 3 y. Why am I not supposed
Be able to handle that factor in the denominator?
Because you can cross each divide. For the y-intercept. Yeah, I was gonna say.
Write down the whole too. If there's a whole.
Yeah,
You can just give the x coordinate if you want. Thank you very much. All right, let's go over this here. Hopefully, most of you had a chance to graph it and all that. I asked them to put this table over here, to put this work up here, but I told them we'd wait to graph it here together because I think some of you might have some question marks about the most efficient and effective way to graph this without a calculator. So certainly to start with, you're going to put down your vertical asymptotes and your horizontal asymptotes, all the information you could possibly know. So go ahead and do that, maybe just dashed here. Okay, here's x equals -2, x equals 3, and y equals 0. And then we don't have very much to plot here. Like we can plot, what's the y-intercept is 1/6. What's wrong? It's just 1. Okay. 1 is the x-intercept. And then right now, I mean, we have all the information down, don't we? Thanks, guys. So now the question is, how would you graph this? There's not a lot to go on. Maybe it kind of looks like this, or does it look like this? I have a little bit of a feel. Obviously, whatever I graph, the curves need to kind of approach the asymptotes asymptotically in that way. So I have a feel that that's going to need to happen somehow. Here's what I would suggest. If you're not sure what happens over here, for example, that is to the left of x equals -2, then plug in a value. Like, let's actually plug in -3 for x and see what we get. And by plugging -3, I mean, let's use this guy right here. And when we do, right now at least, I actually don't care what the y value is. Are you ready? Watch this. If I plug in -3, I get something negative times something negative times something negative times something negative times something negative. If I plug in -3, and therefore I do know something about the y coordinate, even though I've been too lazy to compute it actually. What's the y coordinate? It's something negative, isn't it? So I already have a feel. X equals -3, y is negative. I think that it looks like this. Now, how can I be so cavalier as to just say, well, I think they're all negative, past -2 on the left? Well, because of the horizontal asymptote, you might say, but how do I know that it doesn't go and be positive at some point? Couldn't it have crossed the x-axis over here and gone up above it maybe somewhere else? And then come back down to the asymptote? Why do I know that it can't possibly have crossed the x-axis over here? Yeah, it would have produced another 0, right? And we already know the only place it crosses the x-axis is right here. We already have that. So I know that it couldn't have, if it's negative, it's all negative, okay? The same logic could be used over here. I think you'll find that this is positive over here. Okay, it looks something like that. And then in the middle, I think already these 2 points suggest this kind of behavior, but if you're not sure, plug in a couple points to make sure. Okay? And that's what we get a picture of. We also have a hole at x equals 2, don't we? All right, that's the hole is maybe not quite in the right place. I got a little carried away, but all right. The other thing to notice too is this provides a nice counterexample for those who say, oh, a horizontal. Remember that a lot of you had this misconception at the beginning of the year. A horizontal asymptote can't be crossed. I don't know what to say to you except yes, it can. Like let's move on, right? Like there it is. It's been crossed, right? Huh?
In AF, they tell you it can't be crossed.
Well, then show them this function. Or actually, it's very, very easy to come up with functions that have horizontal asymptotes that are crossed, right?
What's the point of having a horizontal asymptote?
Right, there's another one that has a horizontal asymptote that's crossed, right? It's very easy to come up with one. Yeah. Keep in mind that keep in mind the definition of a horizontal asymptote, right? Is it true that as x gets large, y approaches a number? If so, then we have a horizontal asymptote. Yeah, so we're good. Let's try one. Let's see if we do one here before you leave. We'll do this one together. That has a slant asymptote. Okay. All right. So this is not the interesting part. I'll do this list for you because I think it's not super interesting, right? So we have We have vertical asymptotes at t equals, I guess we're using t, plus or minus 3. We have an x-intercept at t equals 0, and that's also the y-intercept, isn't it? Okay. All right, so already I've got t equals -3, t equals +3, and 0, 0. That's not much to go on, right? But we still have to talk about the slant asymptote on this one. And we've already talked about this. We can do this division problem, so that's what we're about to do. And we're going to do like a rewrite on this to show what the slant asymptote is. I already know that there's a slant asymptote of some kind because the degree is 1 greater than the denominator. That is, when I do this division, I already know the quotient will be something linear, right? When I do cubic divided by quadratic, I am going to, when I do the division, get something linear, right? So I haven't done it yet, but I think I know that's going to happen. T squared into t cubed. This couldn't be an easier slant asymptote, by the way. T squared into t cubed goes t times, multiplying gives us t cubed minus 9t, and subtracting gives us, we actually don't care what the remainder is, but it's 9t, okay? Which tells us that we can rewrite the original function as t plus 9t over t squared minus 9. If you don't believe me, anytime you want to check your division, add them back together and see that you do get the original function. All right, so that's another, we now have in front of us 3 different ways of representing this function. We've got its original form I gave you, its factored form, and then this new form too, which is nice because it shows what the asymptotic behavior is. As t gets large, this becomes negligible, and this function just acts out at infinity, acts like y equals x, doesn't it? That's the behavior this takes on. So we'll illustrate that by actually plotting, just like we do the other asymptotes, the line y equals t. Again, other times you'll have more complicated asymptotes. Other times you'll have more complicated. It might be like 2t plus 1, right? But we'll start with a nice easy one. And then similar logic to the last problem. Like y, the other way this could possibly look is this way, right? Approaching the asymptotes this way. But why again do I know that's not going to happen? There's no other x-intercepts. So I think I know that on both of those it looks like this. If you want to plug in values on the left and right here, I think you'll get that in the middle. And then there's one other thing to notice about this function that might help you. This particular function has a nice unit 1 property. It's a what kind of function? It's odd, which means that might help you graph it too using the symmetry. All right, so division is the word of the day, right? Long division. You can't see it. It's not as similar as you'd like to that, because like I said, it could be that there's not going to be 2, right? So that's the reason